Hello, this is Jennifer Dassinger with A Plus College Ready, and I'm now here with you to go over general equilibrium calculations. If you haven't already, please make sure you've watched and listened and gone over to your notes on general equilibrium basics and Le Chatelier's that might help you in the calculations, but that's not necessary for this one. All right, so let's get down to it. Let's break out our calculators and look at some math. First practice problem is determining K from equilibrium concentrations. So pay attention to the wording. I'm giving moles of my reactant, moles of my product. Notice the phrasing says found at equilibrium in this container at this temperature. Okay, but notice the container volume. Moles, volume. Yes, I'm going to have to calculate my molarity. And yes, I'm going to have to change my milliliters to liters. So if you notice when I write my equilibrium expression to solve for K, my product is over my reactant is raised to the coefficient. Then I incorporate my concentration of the moles per liter. So notice again, you have to do moles per liter. And remember, K does not have units. Okay, so now it's your turn. Here's an example. Pay attention to the wording and pause the video to see if you can solve this problem on your own. Okay, we're back, and here's the answer. So you take your concentration of your product, notice it was in molarity this time, and notice the reactant was in molarity as well, and you raised it to the second power. So notice the lower temperature between the two caused the value of K to be larger, proving that K is temperature dependent. Did you compare and contrast those two practice problems? You might want to again pause the video and look back at that. Next condition. If you change the stoichiometric coefficients of K, let's say by raising the K value to 3, for example, if you multiply the whole reaction by doubling it, you're going to have to square the K. If you triple the reaction, you're going to have to cube K. What if the reaction is written in reverse? Then you're going to have to retake the reciprocal of K. Or if you have to add equations, multiplying them respectively, K1 times K2 times K3. Let's look at some practice problems. So here's a general practice problem where if you notice again that Haber process at 127 degrees Celsius, you're given the concentrations, products over reactants, you solved KEQ. But then notice what happened in the second part. The reaction was reversed. It's no longer forming ammonia, now ammonia is decomposing. So you have to take the reciprocal of 1 over K. And that's why you'll get your lower value of the 1 over K is the 2.6 to the power of negative 5. That's your answer. Then notice at the bottom, what happens if the reaction is halved? Notice all the coefficients are halved. So again, you just raise your K value to the half and you'll halve the amount of your K. Pretty simple. So again, now we're going to look at the difference between Q to K in terms of mathematical problems. Let me just reiterate again, what is Q? Q is when conditions are not at equilibrium. Yes, reaction quotient is written just like a K value, but it's not going to be at equilibrium. So, just a refresher, when K is less than Q, you will have the system not at equilibrium and the reactants are favored. But notice, I just said K less than Q. Watch the arrow. You'll have to flip that in your brain and look and go, oh, that means Q is greater than K. Obviously, Q to K is equilibrium. When K is greater than Q, we're going to be shifting to the product side, right? That means, again, Q is less than K. Look at my Le Chatelier's video and you'll be able to see in PowerPoint notes, and you'll be able to see this little trick there of what is in blue. All right, so let's look at a practice problem. Notice it says the following gases are introduced, hint, 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 key word right there, into a closed flask. They give you concentration, so we will be writing in concentration form with brackets. They give us a K value, so we're going to compare Q to K. So again, products over reactants. You put your product amount raised to the coefficient over your reactant amount, plug it in, and notice our Q value is less than K. So if our Q value is less than K, the equilibrium must shift to the right to achieve equilibrium. So for the reverse reaction that we've been looking at before of this dinitrogen tetraoxide now to nitrogen dioxide, here's our reaction quotient. You'll be given some experimental data. So if you notice, you have initial conditions in experiment 1, experiment 2, there's your Q value. Now look at equilibrium. You have your at equilibrium conditions, 10.4. The tables tell you that Q is different, but that the ratio of K is constant. K is a special value, Q will change. And remember, when the reactant and product concentrations have their equilibrium values, that's when you know you're at K. All right, using the reaction quotient to predict the shift. Let's take that Haber process and look at various conditions. So if you want to pause the video and take your time to plug these in, follow along as I've written the example out for you, you can look at A, B, and C. But obviously I've given you a condition of each one, where in A, Q is greater than K, the reaction is going to shift to the left if the reactant side is favored. B is where the value of Q is equal to K, because K is in, of course, our problem at the top. And then, of course, C, where we have Q is less than K, and it's going to be product favored. Now for some lovely rice tables. Rice tables is where you have to, or ice tables as we used to call them, you have to have a balanced reaction. That's where the R comes in. The I is the initial concentrations written in moles in the table. Determine the change in the initial concentrations, and that's in terms of X. And then the equilibrium concentration expression. You combine the two. You combine the I with the X, okay? Or the I with the C value. So notice the general setup. You write your balanced reaction, you set up your rice table, you set up your equilibrium expression, and celebrate if you're given equilibrium concentrations. Then you can just skip down to E, fill them in, and work backwards to find the change. That's awesome when we find that. The note here is if you look for small k values, then the X will be negligible. In other words, we won't have to worry about large K values in this case. None of our initial conditions or concentrations will be 0. Then Q would be calculated first to determine the shift. So let's look at some practice. So here's where a student is placed 7 moles of ammonia in a flask. Notice again, they're going to make you calculate the concentration of ammonia. So that's the first thing you should probably do after you set up your rice table, and that's what I've done as well in black. So you can see how I found out my 14 moles. So my 14 moles of ammonia is at initial, because why? It says placed in. Then notice the wording, at equilibrium. Notice you have 6.2, so for my nitrogen. So notice on my E, I had to fill in 6.2 in green. What is the equilibrium constant for K? Well, I basically just have to use my coefficients and go from moles of my ammonia to my moles of, my moles of nitrogen to my moles of ammonia. And that's pretty simple. And I've showed you the stoichiometry below. Same thing with my moles of my nitrogen. I can calculate my moles of my hydrogen. Do the math. Then all I have to do is fill in my K expression at the bottom in blue, and of course solve for K. Now you try. Pause the video for a minute and practice this problem, and then we're going to check your answer. Okay, we're back. Check your rice table. See if you incorporated your initial conditions that I have there in black. Notice that the red is in change. I have to bring down my coefficients. Then I have, of course, my combined initial with my change for my equilibrium expression. I plug it into my equilibrium expression with my k value. Let's go to the next slide. And then I have to literally solve for x. Combine like terms and simplify and then solve for x, and that's my molarity of the 0.530. Now, if I want to find hydrofluoric acid, I have to multiply that by 2 to get its molarity. Here's another example problem. Take your time, read the question, see if you can set it up. Pause the video now and see if you can figure this out. So we're back. This one was a little challenging. It had two equilibrium statements. It had at equilibrium and then when equilibrium was reestablished. So there's two E's, if you would, here, and I color-coded them for you so you can be able to figure it out. So, but essentially, when you added that 5, you have to calculate the molarity of hydrochloric acid. I've showed you there. And then that way you've got your moles of your hydrochloric acid. Then, if you notice, I've taken your K constant at original equilibrium and equilibrium at the final, plug it in, and then I solved for my x value. Take a moment and walk through those steps if you're still confused. Here's another way to double check your calculation of the chlorine though when equilibrium is reestablished, and this works to solve for K. So plug it back in. Take that 6 molar plus x equals 6 molar plus 2 molar to 8 molar. Therefore, I incorporated my 8 molar minus my 4 molar solution with my 6 plus the 2, raise those both to the coefficient, and yes, I was able to get the same response as before. This is the most complicated equilibrium calculation that you're going to be able to see. So if you can do this, you can do any of the rice tables thrown at you. At this time, I'm finished with showing you all things equilibrium calculations. Stay tuned for our solubility of equilibrium PowerPoint and note calculations. But at this time, my best recommendation is to practice, practice, practice. Work on those practice problems, get more practice problems from your teacher, and good luck on the exam.